Orion. NASA's next bold step to advance human space exploration is preparing for its first major demonstration, Exploration Flight Test 1. It's bigger than Apollo, more flexible than the shuttle, but is it ready for deep space? Or does the co-host have other plans? Find out on NASA Edge.
I got to tell you, it's kind of interesting. I'm sitting here looking at this thinking, wow, it's amazing to be here in front of Orion, but this has got to be a real milestone for you and your group.
It's really something. There are 14 different subsystems that all come together. They're all going to pass through this building to make this spacecraft what it needs to be. This is just the first element, which is the primary structure. And yeah, we've got efforts going on all across the country with really smart people. They're carrying a heavy load to make sure that all that stuff gets here. In the next year, it's really going to turn into a spacefaring vehicle.
Well, and that's what I was going to say. So everything now, at least from what I understand, will all take place here. Everything will come here and be installed on Orion.
That's right. So all the subsystems are really being designed and fabricated in other parts of the country. They come here to be installed in this crew module.
I don't know, call me crazy, but it seems like it's perfect for someone like my size, for me to command this kind of module. Do you design it for somebody my height?
Yes, we do.
See, the built-in parameters for me.
Built-in parameters, we can accommodate for anywhere from you to the Jolly Green Giant.
Oh, well, see, now that's what I don't want. I was hoping it would have to be custom-made for me, so,
You would be more comfortable in here because, the habitable volume, while it's a lot larger than Apollo was, if you think about the mission duration, it's still a long time to be in there as your primary living quarters.
Well, now, we are still a ways away from human flight in an Orion, correct?
Yeah, we are, but we could be closer. So we're going to pay as you go, and This will be a demonstration of all of our critical systems. In 2017, we've got people that would be pushing for that to be a human-rated mission as well. And we've got people that would actually like to put an astronaut on it. We think it'll be safe at that point in time. But we set our sights out a little bit further than 2017 and are really looking to get that off as our next mission.
Well, now, are you still taking requests for options to add, like, coffee makers or certain amenities that might be helpful in space?
We are, but, we have a mass target to meet, and that mass target is really pretty tough for us to do so that we can get all the crew and all the provisions for a very long duration mission. So the crew module that you see here, the next version will have to be lighter and even closer to the mass targets that we need to be able to accommodate all the human systems that we're going to put on.
Actually, when this launches in 2014, you'll still be making improvements and maybe exceeding your requirements by the time we fly in 2017?
I think the best way to say it is that we've been a relatively skinny program. And at this point, we're going to take this spacecraft and we're going to test it to find out just where the margins are.
Okay.
And then we'll be able to take advantage of that in the next iteration to get those margins out, because we want every pound that we can get to be able to accommodate the crew.
So at least you feel good, like you have room in subsequent versions.
We do. It's good to start off a little heavyweight and then you could go on your diet.
Yeah, slim fast for the Orion. Guys, I'm very proud to introduce you to my latest and greatest acquisition. Be careful, there are active tools on the ground, a crew.
Hey, 3-1, it's a Lego startup kit.
Probably.
Hey, Franklin, that is not Captain America's shield.
Wow. Can you believe it?
No.
Impressive, isn't it?
What's this?
Gentlemen, I want to present to you the centerpiece of CFT-1 CoRion.
CFT-1?
Co-host flight test.
One?
Well, it's the first.
Wow.
The more important thing is CoRion, co-host Orion. I've taken all the technology from Orion and implemented it in my own flight test article.
Where'd you get all this metal?
Yeah.
Let's just say I'm going to need to write into Word from you guys, if that's okay, in the future. Had to scrounge a little bit.
Even work the parachutes in here?
Parachutes, interesting. Yes, certainly an important part of CFT-1, so I'm sure that there's some space to integrate that.
You know about parachutes?
Yeah, I actually talked to Stu McClung down at the Kennedy Space Center, and he talked to me a little about how they are integrating parachutes into EFT-1, which looks very similar to CFT.
Yeah, CFT, or the CoRion, and it does look similar because it's modeled closely on Orion. And I look forward to learning a lot about the parachute technology and integrating it.
Heat shield?
After the true coat.
How has the parachute system evolved since the beginning of the Orion program to where we are today?
When we first started back in 2006 to where we are now, we've had a few iterations. The basic numbers of chutes is the same. The main parachutes have gotten slightly larger. We adjusted them for vehicle mass, but to the outside eye, I don't think you'd notice a change. As we've done all of our development tests, we've done things to improve the reliability and the safety of the deployment. We had a device called a torque limiter. We ran a series of ground tests and realized we didn't need that in the system. We took that out. It made the system more reliable by making it safer. We adjusted the porosity. We added some holes to the chutes to make them a little bit more stable. We used to have where the risers come up to the bottom of the parachute, you'd have a fitting that was called a knuckle. It was a big metal mass. When you throw a big metal mass out of the back of your spacecraft, it can knock around and hit things. We came up with designs called soft links that eliminated that large mass jumping around. And so every time we run a test, based on what we learn, we tweak the design to make it a little bit safer, a little bit stronger.
Well, you have a 20,000-pound capsule, but you don't have it yet. How do you test parachutes to slow something like this down?
So we've built a couple of test capsules that give us the same characteristics. We have what looks like a big giant dart, and we also have a capsule that looks very much like a finished Orion. It's a little bit shorter. You put it on a sled, and you let it go out the back of a C-17.
20,000-pound version.
20,000-pound vehicle out the back of a C-17 with some parachutes to extract it out, and gravity always works. And once it's out of the C-17, it's separated from the sled that it sits on, starts to fall to the earth, and that starts our parachute sequence. And so we use either the DART or the test vehicle, depending on which type of test we're running, to help prove out that the parachutes are going to behave the way we expect.
Can you kind of walk me through how parachutes will work on Orion when it re-enters the Earth's atmosphere?
All right. You've come through re-entry, you're in the range of 25 to 30,000 feet altitude. Based on computers, parachutes.
I'm going to slow you down real quick. So the Orion capsule is down where like aircraft actually fly before a chute is deployed?
That's correct.
Wow.
Yeah, we've ridden down, I always like to call it, we've surfed down through the atmosphere. Till about 30,000 feet.
Okay.
The first set of chutes are called our forward bay cover parachutes. They are deployed by a mortar, and so the parachutes are packed in a mortar tube, and there's a gunpowder charge in there. The computer says fire. All three of them receive the command, and the three parachutes are shot out of the top of the mortar, and they inflate real quickly. We fire some bolts, and that basically takes the forward bay cover away and gets it away from the vehicle. Immediately after that happens, the two drogue parachutes are fired through a mortar, and the drogues are 23 feet in diameter. They slow the vehicle down. They go through their reefing stages, which they open up in stages so they don't overload the chute or the vehicle. And you ride the drogues for a little while until you've slowed the vehicle down to the right point, cut them away, and then the three pilot chutes are fired out, and they're actually attached to the three large main parachutes, and then they pull the three main parachutes out of their bays, and then the three chutes go through their reefing sequences, and by about somewhere between 5,000 and 10,000 feet, we're under full reefing and just ride them all the way to the ground.
At the Langley Research Center, we saw some testing of when the Orion model hit the water, it actually flipped over.
That's right. The Apollo history is that happened about half the time. When it's upright, we call that stable 1. If it turns over like you described, that goes to stable 2. So we plan for stable 2 happening. If it happens, there are 5 airbags that are installed in 5 of the 6 gussets in the forward bay. They stay there the whole mission. Once the computers sense we've landed, they actually cut away the main parachutes and then issue a command for the high-pressure gas that's been stored to blow down and inflate those 5 bags. And the change in buoyancy just by those 5 bags inflating causes the vehicle to rotate and pop back up to stable 1.
And they're only going to inflate if it's in stable 2?
It'll actually, the way the software is written right now, it'll inflate in either case. And you do it that way if you happen to have an abort and go into the Atlantic Ocean, like into the North Atlantic on a high altitude abort and land in rough seas for some case. Unlikely event, but if you did, you go ahead and inflate the bags because it helps ensure that the vehicle wouldn't, in a bad wave, want to tumble back around.
Gotcha.
I got the parachute.
Okay.
but I'm a little concerned about buoyancy upon re-entry.
Buoyancy?
Orion. Yeah. Water landing. It's got to be able to float.
Well, wait a minute. How are you going to get it off the ground?
Launching, I do need a launch vehicle. I need propulsion, yes.
And what's your destinations? Where do you want to go beyond low Earth orbit?
The best thing to do here is to look at Orion and sort of like follow on their
Space
coattails.
station, asteroid,
Possibly.
Mars.
Speaking of the future, Chris knows a guy.
Yeah, Josh Hopkins from Lockheed Martin. He's sort of the genius behind looking at the flexible path and looking at all the different options that Orion can take. And maybe you can kind of tag along with that approach and see if you can come up with your own destination.
First, I need a flexible path about how I'm going to get this flight test article out of the garage. Like maybe I go through the door, maybe I go through the window, maybe I lift the garage. I've got lots of options that I got to figure out before we move forward.
I don't
Maybe
know.
buoyancy isn't my biggest problem.
One of the missions that we're thinking for Orion is that we may use it in conjunction with another spacecraft, maybe another second Orion, to go to a near-Earth asteroid. And that's something like a 6-month trip. So obviously it's relatively small spacecraft. It's a fairly cramped mission. We're interested in how do we make that mission as short as possible. So one of the things we've been focusing on is how do we find the asteroids that are the easiest to get to,
Right.
that we can get there, spend as much time as possible, and come back in just a few months.
And how are you able to track those asteroids, years and years down the road?
Yeah, that turns out to be one of the challenges. There are programs in place at various observatories to discover asteroids, particularly the ones that might be hazardous, but there's not a strong program to continue tracking those. And we need to track them over weeks or months or years to really pin down their orbits and also to characterize what they're made of, how fast their spin rates are. And so there's actually a group of volunteer astronomers, essentially. Some of them are at universities, some of them have telescopes in their backyards. And we work with them, they work with each other and with NASA to figure out which ones to prioritize and to try to track those as much as possible.
You're saying that you may have 1, 2, or maybe more spacecrafts.
Right.
So is the idea is to develop a bigger spacecraft for Orion to dock to, they go onto the asteroid, and then Orion will come back by itself?
Right, that's one possibility. One of the things we're trying to figure out is how does an asteroid mission fit into a sequence of initial test flights and then early sort of steps out into deep space and then the asteroids and then eventually leading on to Mars. So depending on the sequence, what you might do is a relatively near-term limited mission with just Orion type spacecraft, or you might use that flight as a way of testing the bigger habitats that you're going to need for a Mars mission. So even though those might be, bigger than we need for a 6-month asteroid mission, we want a way to test fly those and work out the bugs before we commit astronauts to a 2.5-year trip to Mars.
Essentially what we're doing is we're going back to sort of the days of Gemini and Apollo, where we're doing a series of missions leading up to the actual launch where we're going to have humans actually going to an asteroid and conducting scientific research.
Yeah, I think the analogy to Gemini is a very good one. Back then we identified that we needed to do things like figure out how to do rendezvous and spacewalks before we could do Apollo. And Gemini was the program that basically figured out how to do that sort of thing. We know that we need to be able to keep people safe for something like 6-month trips into deep space or a year into deep space for asteroids. And so one of the things we want to do is start doing deep space trips just beyond the moon to the Earth-Moon L2 point.
Yes, the Lagrange point.
Right.
And what is the Lagrange point?
Well, a Lagrange point is basically a neat little trick with physics to be able to make something like a spacecraft or some other body orbiting in this Lagrange point to be synchronized with the Earth and the Moon, say, or the Sun and the Earth as they go around in their orbits. So there's a L1 Lagrange point that's on the near side of the Moon and an L2 Lagrange point that's beyond the far side of the Moon. If we put a spacecraft at that L2 point, it basically stays over the far side of the Moon as the Moon's going around the Earth. So we have continuous visibility to the interesting science locations on the far side, but we can also see Earth continuously as well.
So the cool thing is that we can actually park a spacecraft in
Right.
an Earth-Moon L2, leave it there, resupply it maybe every couple of years or so,
Right.
and then when we send astronauts, all the supplies will be there when they arrive to that spacecraft.
Right, within Lockheed Martin, we've looked at an initial flight that would send just an Orion to there and spend about 2 weeks orbiting and come back. Or you could envision something like a miniature space station there where you could send crews temporarily and they could control robots on the lunar surface.
Is there going to be a point, let's say, of no return where the astronauts are going to be on their own for a while they're in
Yes.
space?
One of the big things we have to learn how to do for a Mars mission or an asteroid mission is we have to learn how to get comfortable with the idea that the astronauts can't just come home quickly in an emergency. During the space shuttle and space station programs where we're in low Earth orbit, There's a variety of contingency failure scenarios like that where basically the plan is go home as fast as you can. But when we are something like at L2, we might be, say, 7 to 10 days away from Earth. At an asteroid, you could be 60 or 90, 180 days away from Earth. So you can't just count on being able to get back quickly. You've got to figure out things like how do we prevent those failures from happening in the first place, and how do we fix them on board. The other problem is that if we're at an asteroid, it might take something like a minute or 2 or 3 for radio signals from Earth to get to the crew. You know, one of the things we've traditionally done in human spaceflight is the astronauts are really smart, they know a lot about their spacecraft, but there's a lot of things that they rely on for the ground back in Houston to be able to keep an eye on or remind them of procedures, for instance. So we have to figure out ways to bring more of that capability up onto the spacecraft.
And thinking about that spacecraft that's going to be in L2, I guess you're not so worried about time, right? Because if you can send a spacecraft that's very low energy,
that doesn't have the astronauts on board, it can take more time.
It can take more time, whereas once you have the astronauts, you've got to get there and get there as fast as you can. But also try to save as much energy as possible too, right?
Right, so one of the things that's interesting about using Lagrange points is that they might be good places to assemble the spacecraft for deep space missions. So you may be able to use slow, efficient propulsion to kind of climb out of the Earth's gravity well, but you're not going very far. So when it's time to launch the crew, you can get them to that assembly point in a few days, and then you've got your whole system ready to go out to a more distant destination.
You know, Ryan is making some great strides. I didn't even realize this whole Lagrange point thing. I'm going to have to hit Wikipedia. I don't even know what that is.
Yeah, make sure you study Earth, Moon, L2, Lagrange point.
L2.
And make sure you double check your references before you start quoting stuff.
Yeah, I've gotten burned by that one before. Anyway, I'm feeling a little behind schedule here with CoRion.
I wouldn't get discouraged because, you know, NASA didn't start with manned spaceflight a couple of weeks ago. They've been at this for a few years.
Hey, and especially with EFT-1, I mean, they've been working on this for a while, and they're on track for the 2014 flight test.
Still, I want to make a big splash. I want to make a big impression.
I tell you what, my advice to you is make sure that CoRion is not identical to Orion. Make something that stands out between the two.
Now, you mean something different other than just like adding racing stripes. You mean something substantive.
Absolutely.
Yeah, so for example, why not break the Kessel Run in 12 parsecs?
Impressive.
Most impressive.
Well, if you guys think that's impressive, wait till you see my next project.
So Jason, I understand that you're the Q of NASA.
Well, that's an interesting reference in itself, but it's a nice analogy. If you think about Q was getting ready for Bond to go off and do whatever mission he was being charged to do. Our group is much like that. We're designing all the systems to send our crews off to explore deep space.
Now, within your portfolio or your technologies, what are you trying to develop?
So, a couple fundamental things. You need to be able to get into space, you need to be able to live in space and be productive when you're there. So we're building a lot of the stuff that allows you to live in space. So we are developing some of the next generation habitation systems. So where's the home? How are people going to live in that? Life support systems for it, how are you going to handle logistics and management of that overall being able to live in space?
Now, I guess, like, let's say when we go to Mars one day, we have the first humans on Mars. The first thing that comes to my mind is going to be spacesuits.
Absolutely. So we're also advancing the new spacesuits technologies. In spacesuits, we see you have what you see on the space station today. They go out, they repair something, they fix something, they come back in. On a trip to, say, Mars, you're going to potentially have to go out, fix things along the way, long duration there, and then when you get to the surface, you want to go outside.
Right. Now, one of the cool labs we have here at NASA Johnson Space Center is the Portable Life Support System Ventilation Laboratory, and that's where they're working on the spacesuits of the next generation.
Correct, yeah. So the suit is made up of two parts, the actual garment that you wear and then the backpack, the portable life support system. The life support system, the one we have, has been very reliable. However, it's getting pretty old at this point. And there's a lot of new technologies that we want to actually incorporate in the backpack of the future. For assembling the space station, or what we did on a shuttle, you're working in zero gravity, in near zero gravity. So the weight of the suit didn't really matter as much, the mass of the suit. But when you get to a surface, even though with the reduced gravity on Mars, you're still going to have to carry around that weight. So you're going to need a lighter weight suit, and also one that you can use more frequently, and also the one that puts up with the environment, the dust, the rocks, and all those kind of things. When we did those short duration EVAs during Apollo, we only did a very few number of them, and we were there on the surface of the moon for a very short time. On Mars, we're going to be there for a long time.
Mobility will probably be an issue. You said weight's an issue.
Yeah.
The flexibility of actually working in that environment would be a key factor.
Correct, yeah. So a lot of the station assembly, they optimized the suit to working on the space station. So your work zones and such, you're not picking up things off the ground, you're not using hand tools and those kind of things. Instead, you're turning bolts and all that. So you have a different type of work that you're going to be doing.
Now, is there something with that backpack, is there something that you want to try to miniaturize it, to make it as small as possible? But on the flip side, you want as much oxygen for the astronauts to breathe to stay out there for extended periods of time on the surface.
Yeah, so you have this hard challenge of wanting to be out there as long as you can be out there and making it as lightweight as possible, which is what most people can relate to if anybody's ever traveled. You don't want to be carrying around a big, heavy bag all the time either. So.
That's right, that's true. Now, what are some other cool technologies going on?
One of the problems we have is managing all the logistics. If you're going to be gone on a trip and you pack your car and you need to figure out where everything is going to be in, say, your motorhome over the course of a couple of years, how are you going to find all that stuff? So what we're going to do is use next generation RFID, or what we call radio frequency ID tags.
Okay.
And what those allow you to do is wirelessly track and inventory where everything is inside of your vehicle.
That actually makes sense because, especially you take a look at something like ISS, where you probably have thousands and thousands of pieces of equipment on station, and how you keep track of all that.
And on space station, we don't sometimes. There are a number of items that we've lost on the space station, and we have to potentially fly a new one up. On the space station, you have the additive benefit of the crews changing every 6 months. So imagine if you were living in your house for 6 months, you put everything where you wanted it to go. Somebody else comes up 6 months later and moves it all on you. And then you come back again, and nobody knows where everything went.
Right.
So everything will have the equivalent of almost like a high-tech sticker that actually tracks every piece, and you'll have different types of readers. So you have readers that are in between modules, so you can track when something moves from one module to another, and you'll have other readers that may be handheld, so you can scan your storage bags and figure out which bag is it exactly in. We're even looking at how do you make one of those scanners and put it on one of our flying robots.
Like spheres?
On spheres.
Oh, okay. Yeah.
So we're actually going to test a mobile RFID reader where you actually attach it to the robot and let the robot figure out the inventory. It can go out and manage and inventory where everything is. The crew actually doesn't have to do that kind of mundane task. The robot can actually go off and do that. And in fact, our space technology mission director colleagues are starting the development on that robot that will follow on after Spheres, and its name is Astrobee.
One of the cool technologies that we've been watching closely is the additive manufacturing, our 3D printer. We have one on the station now.
Yeah.
How's that coming along?
So we're talking about all these parts and pieces that you want, and you try to predict everything that would ever go wrong. Well, we're going to not think of some things. So one of the advantages of additive manufacturing, if we don't have a part, we can just order it up and have folks here on the ground design it digitally, email the file up, and then print out the part on orbit.
And how long is that process in terms of making a tool or making a piece of technology?
So on station, we've already printed over 20-some parts. And in fact, you can print several parts per day, whatever you want, just on a single printer.
Today we're at the Additive Manufacturing Lab at the Marshall Space Flight Center, and I'm talking with the 3D Printing in Space project manager, Nikki Werkheiser. How you doing, Nikki?
Hi, doing well, thanks.
Additive manufacturing, exactly what is it?
So additive manufacturing is actually the kind of formal term for 3D printing. Traditional manufacturing is subtractive. You have a material and you take away from it. Additive is any process really where you actually build the part that you're trying to create layer by layer. So it's additive instead of subtractive.
3D printing has been around for a long, long time. So why is it right now we're talking about doing 3D printing in space?
So 3D printing, you're correct, it's been on the ground for quite some time. But as you probably know, in space travel, we depend on flying every single thing from the ground to the space station, for example, that we might ever need. So our supply chain from the inception of the human space program has really been quite limited. But when we really start to think about exploring further out destinations like Mars or asteroids or the moon, that supply chain model really isn't feasible. We have to think about how we would respond in real time in a sustainable, affordable way if parts get lost or broken. If we're doing science, for example, just like in a lab on the ground, we have disposable hardware, sample containers and syringes, things like that, that right now we're completely dependent upon launching from the ground to space station. So being able to create what you need when you need it on these type of missions is really a critical enabler to sustainable, affordable exploration missions.
Well, I've seen 3D printing work here on the ground, but to get it in space, what are the technology hurdles that you have to get over to make sure it works the same way in space as it does here on Earth?
Right, so those were actually our exact questions. As a matter of fact, it was back in 1999 that Ken Cooper here at Marshall Space Flight Center flew the first 3D printer on a parabolic flight to see how it would react to microgravity. Since then, the company Made in Space, which we have a Small Business Innovation Research Award with and actually built the 3D printer that we've launched to space station now, has flown over 500 parabolas on those flights through NASA's Flight Opportunity Program. So from that, we've gotten some really good data. We've been able to see in microgravity the basic response when you're laying the layers and performing additive manufacturing. However, you only get the 20 to 30 second spurts of microgravity on those flights. So the bottom line is that the space station is actually the only platform we have in the entire universe where we can test this process out and print a complete part in microgravity. And that's why the first printer that we just launched, it is the first 3D printer ever in space, and we launched it on SpaceX 4 recently. That's why it's called a technology demonstration.
Now on the table right over here, we have a replica of what is flying on the ISS right now. Exactly how does this 3D printer work?
So this first printer that we're flying, we're actually operating in the microgravity science glove box. And that is because since this had never been done in space before, we did not have all of the data for things like flammability and off-gassing of the heated extruded material that we're printing with. Since then, we've collected all that ground data and found that actually the results are promising. The next printer will actually operate outside of MSG. We'll have a next generation that's based off of what we've learned off this printer. We've already learned a great deal. When you're designing something for space flight, you actually need more automation than you have on the ground. Astronaut time is very valuable and limited, so you want to be able to automate. You also want to be able to control it remotely from the ground as much as possible. So you'll note, for example, that we have 2 large windows in the printer, and we'll have cameras aimed at those windows during the printing process. And we will be able to see in detail as the layers are being deposited how that process is unfolding. What's really exciting about this is we can actually email our 3D print files directly to the 3D printer from the ground to space station. So it sounds very kind of science fiction, but it's not. It's going to be science fact very soon.
Tea Earl Grey hot.
What material is being used in the production of the parts that are going to be made on the ISS?
Sure, so for our first printer, the technology demonstration, we're actually using ABS plastic, which is the same plastic. If you see here, this is a little piece of the filament. This is the same plastic that Legos are made out of, for example. Mm-hmm. The filament that we use is just like this, and to be quite honest, it looks almost just like your weed eater spool. Mm-hmm. We're actually looking at the next generation printer as well for even more materials, stronger plastics, for example.
You talk about plastics, but when we get down to the point where we're talking about tools that break, sure. What is the future for using metals in space and building those type of tools?
Right, so at NASA we actually have what we call the In-Space Manufacturing Initiative. And that initiative actually is composed of a roadmap or a vision of all the integrated suite of capabilities that we'll really ultimately need for exploration missions that we want to test on space station. We also want to do things, as you mentioned, like printing with metals in space, printing electronics as well. We actually, last year, NASA released a small business and innovation research proposal for a recycler on how to take that 3D printed part and turn it back into usable feedstock.
Nikki, what are the goals of this technology demonstration on the ISS?
So for the technology demonstration, it really has 2 phases. And the very first phase is specifically just to answer the question, does the additive manufacturing or 3D printing process work in microgravity the same way it does on the ground? So for the first phase, we'll actually be printing a lot of parts that may not look super exciting to the layman, but are very exciting to us. We'll have coupons. So we'll have things that look like this. This is a tensile specimen. We'll be doing things like compression and flexure and torque. For those parts, we'll be watching from the ground as the parts are printed through the cameras live. So we'll be able to tell a lot of information and data we'll be able to see immediately. However, to really determine that, we'll be flying those very first parts, those coupons, we'll be flying those back to the ground And we have printed those same parts on the flight unit before we launched it. So we'll be doing some detailed engineering analysis and testing to compare those parts. Once we have established that the 3D printing process does work the same in microgravity as it does on the ground, we have a second phase. And how I like to think of that is the first phase really focuses on the printer and the printing process. And the second phase, we actually turn our attention more to the parts that we're printing. So utilization parts, we have a broad range, and we're developing a utilization catalog. You can have things like sample containers, small hand tools, replacement parts for exercise equipment or medical tools. There's just a plethora of different areas and categories we're looking into. But the thing there is to learn how to design these parts and build them in microgravity and to create kind of a certification process. We've never actually made the parts we needed in space. We've launched everything from the ground, so we have a very well-known process for how we handle things like safety and flight requirements. So it's kind of fun to start thinking how we would certify a part that we actually built on Space Station. So those are the things we'll be working in the second phase of the technology demonstration. One example, we had a payload on orbit, and you have to change filters out as a requirement every so often, and it was time for the filter exchange, and the filter cap was missing. It's a real simple little part. We were able to 3D print that on the ground in about 45 minutes. Of course, we didn't have the 3D printer on board when this happened, so they actually had to wait 6 months for the next supply ship before they could use that facility. Even though that wasn't a life-threatening example, it's one that has very real and meaningful implications to the science and to the daily operations on Space Station.
What's going to happen in the next generation of 3D printing in space?
Yes, so we're already working that, and everything that we learned from this technology demonstration, including what we've already learned from the design and the operations, getting it ready for flight, will feed into the next generation printer. The really exciting thing about the next generation is that it's going to be a commercial printer. It's called the Additive Manufacturing Facility, and it's being developed by the company Made in Space, and they're out in Silicon Valley. So it won't just be NASA or the government that has access to 3D printing parts in space. It will be available for use by industry and academia, small businesses, large businesses that are interested in making something in space. So I think it's very exciting to think about kind of opening that door and opening the door to the space station and able to manufacture parts in space to more people than just directly NASA.